Okay, so last bit in this chapter about flux correction. Obviously, flux correction is related to this. What am I doing? Is related to the drift, and because the drift is because of the energy imbalance, which relates to ocean and atmosphere, the partition of the energy, northward transport of the energy, and all being slightly off and taking a long time. So there are two things to remember: that the models can balance the top of the atmosphere energy with all the biases and uncertainties, biases inside the ITCZ, reversed gradient in the Atlantic, and so on, that we talked about. But it can also drift, in the sense that balance can remain in the energy and the global mean temperatures can keep drifting. So there are two issues that you should remember: the biases and then the drift. Okay, so the philosophy of flux correction, as we mentioned, is related to this idea that the different fluxes with the flux correction in climate models depend on data which are measured climatologies. So the mean or distribution of sea surface temperatures, atmospheric temperatures, distribution of rainfall, etc., have a climatology, and then there are various variabilities on top of that, and you assume that the flux correction is going to be made, the chopper going by, is going to be made towards climatology, so that given the solar radiation at the top of the atmosphere, the system has a climatology that is realistic as estimated from observations, and then you look for variability on top, like El Nino, or even the anthropogenic increase and the trends and so on and so forth. So for that you rely on observations to estimate observed climatologies. So here is the ocean and the atmosphere again, and the ocean gives a flux to the atmosphere. Atmosphere integrates and does what it does and provides the information back to the ocean. But in terms of what the atmosphere sees and what the ocean sees, one can use observed ocean state and the atmosphere that is simulated to give it the fluxes, and the ocean can take variables that are modeled and observed. Okay, so let me make sure I'm using the terminology correctly. Oops, sorry about that. So we look at the models and the biases, and we say there is a ocean to atmosphere flux that is produced, but then you have uncoupled atmosphere and what it should see. So you take observed, based on measurements, so you take ocean state from measurement. For example, modeled ocean sea surface temperatures may be not very accurate, so in that case you take measured ocean temperatures and give the uncoupled atmosphere some data-based fluxes instead of the ocean, or you correct the model fluxes with observed ocean state to give it a flux correction. That's what is called flux correction. Similarly, you take what the atmosphere produces and replace the atmospheric state with the measured atmospheric state to give the ocean the uncoupled fluxes that it needs to see. So there is a coupled flux that is produced by the ocean atmosphere model, and there are corrected fluxes that the ocean sees nudged by measured atmospheric data, or conditions like humidity, could be various other parameters, and the atmosphere sees what the uncoupled atmospheric model requires by blending measured ocean conditions to give it a flux. And so you end up with essentially uncoupled ocean atmosphere fluxes and coupled ocean atmosphere fluxes. This is what is called flux correction. Sounds complicated, but essentially it is like this. The ocean sees a ocean atmosphere flux, that is what the model is producing, plus a correction which depends on uncoupled ocean flux, so what the ocean actually sees if it is not coupled, because that is taking in some measured atmospheric quantities to produce that flux, minus the uncoupled ocean and atmosphere fluxes. And what the atmosphere sees, on the other hand, is a correction that is coupled ocean atmosphere flux plus a flux computed with measured ocean quantities and uncoupled atmospheric quantities, minus the flux that would be seen with uncoupled ocean variables and uncoupled atmosphere variables. Okay, so this is the ocean flux correction, and this is the atmosphere flux correction, so that you prevent both of them from drifting. There are also other ways of doing this, where you take separately prescribed climatology of the coupled model, and the fluxes are only exchanged for the anomalies or the deviations from that climatology that doesn't change. So that way you also avoid the drift of the climatology. These are all strategies, basically post facto corrections to model biases. So just be aware of those. If you don't understand the details, maybe you don't need to worry, but if you are going to do modeling, obviously you have to go and figure out more from other sources than this introductory course. Okay, so here is how the heat flux correction would look like. This is correction of the heat flux, particularly in areas with strong oceanic currents like the Gulf Stream and the Kuroshio, as well as in areas of deep water formation up here and down here. So you can see that in the other regions, the East Pacific has big biases, so you see some large fluxes there. This has large biases, and you see big fluxes there. And these biases may not be necessarily due to errors in sea surface temperatures in situ, but it could be because the Gulf Stream that is bringing the warm water, instead of going here, it's going here and creating big differences in sea surface temperatures just by shifting the pattern. Whereas here, the upwelling is happening in the right place, but thus the upwelled temperatures are much colder than observations, whereas here temperatures are shifted with respect to the observations because the Gulf Stream or the Kuroshio is separating in the wrong place. So dynamically the reasons for the biases can be different, but the flux correction is done the same way anyways. So here is correction of the water flux in meter per year, particularly in areas with strong oceanic currents like the Gulf Stream and the deep water formation sites. Okay, this is a very coarse resolution model, as you can see from the grid here. The continental outlines are very, very rough, which means the model resolution is very rough as compared to here, for example, or the previous diagrams we saw. Okay, so here the evaporation minus precipitation from the model is compared to some observed estimates, and then the model is nudged using these flux corrections, but instead of heat you are nudging salinity and precipitation and evaporation and so on. Okay, it depends on how it is done. Okay, so that is flux correction. Obviously, as I said, they are not being used anymore, but for historic purposes we are introduced to them. And as I said, it's possible that because the chronic biases in coupled models continue to persist somebody may end up trying flux correction to see whether that changes the 20th century and 21st century projections dramatically or improves them in any sense for the 20th century, which may give us more confidence in the 21st century. After the consequences of bias correction have been figured out. There are reports or papers that have compared simulations with and without flux correction, and they show that for short integrations like multiple decades, flux correction doesn't change the basic simulation too much. So maybe for the time scales of climate projections we are doing at multiple decades, doing flux correction is not worth it, especially because it basically removes the purity of the model. Internally, if model is doing its fluxes given the top of the atmospheric radiation forcing, then at least you know that it's dynamically consistent with itself, it's trying to conserve energy, mass, and so on. But by adding sources and sinks of fresh water and heat with flux correction, you are going to remove that purity. Then interpreting the results also has to be done much more carefully. So let's leave that here and close out this chapter. Okay?